Welcome to This Explainer. Okay, today we're taking a process that honestly kind of feels like a giant chemistry headache and turning it into a really satisfying, totally logical puzzle. If you've ever just stared at a massive jumble of chemical symbols and thought, how in the world do I make this math actually work? Well, you are in the exact right place. We're going to break the whole thing down step by step so you can balance any chemical equation with total confidence. So let's dive right in by kicking things off with a massive fundamental question. Can matter actually be created or destroyed? You see, when we're looking at an unbalanced chemical equation, we aren't just looking at a tiny math error on a piece of scratch paper. Nope, it represents a literal violation of the laws of nature. You absolutely cannot have an atom of iron or oxygen just magically poof into thin air during a reaction. And you definitely can't have a brand new element just pop into existence out of literally nowhere. It's chemistry, right? Not magic.
And honestly, that brings us to the ultimate why behind all the math we're about to do, the law of conservation of mass. Basically, matter cannot be created or destroyed in a chemical reaction. Every single atom that's present at the starting line of a reaction absolutely has to be there at the exact finish line. They're just getting rearranged into brand new molecules. Think of it like a giant bucket of Lego bricks, right? You can completely take apart a toy spaceship to build a toy house, but at the end of the day, you still have the exact same number of blocks sitting there on your floor.
Now here is the absolute golden rule of balancing equations. You gotta know the vital difference between a coefficient and a subscript. On the left side here, we've got coefficients, like that big 2 sitting right in front of H2O. These act just like multipliers in math. They just change the overall quantity of the whole molecule. But on the right side, we've got subscripts, like that little tiny 2 tucked inside H2O2. Subscripts are literally baked into the molecule's identity. You can play around and add coefficients all day long to balance out your scale, but you must absolutely never, ever alter a subscript. If you do, well, you've just turned regular drinking water into hydrogen peroxide, which is a totally different, definitely do not drink chemical. So, to make sure we never accidentally break that golden rule, let's walk through the official, scaffolded method for tackling these equations. By following 4 really simple steps, drawing boxes, listing out our atoms, balancing them one by one, and then doing a final check, we guarantee that we won't get overwhelmed. Even if the reaction looks super complicated at first glance, this structure is your ultimate safety net.
Let's test this out on our first trial equation and see how the whole process builds. We've got iron reacting with water to form iron oxide and hydrogen gas. Now I want you to mentally picture the left side of this arrow, our reactants, and the right side, our products, as a physical scale. Right now, that scale is tipping wildly out of control. It is definitely not in equilibrium.
Let's visually tally up that initial imbalance. If you look at hydrogen, it's actually looking perfectly fine right now. We've got 2 on the left and 2 on the right. Awesome. But look at the iron. We only have 1 on the reactant side, but 3 on the product side. And oxygen, oh man, 1 on the left and a massive 4 on the right. These are the chemical monsters we need to tame to bring this entire equation back into perfect harmony.
So step 1 of our framework, we're going to draw literal boxes around the compounds. Why do we bother doing this? Well, it's a brilliant visual reminder that we absolutely cannot change anything inside those boxes. Those subscripts are basically locked away in an impenetrable fortress. Our coefficients, they can only be placed on the outside of these protective barriers. It completely stops us from accidentally changing the actual chemical identity of the molecules while we're crunching the math.
All right, let's tackle that oxygen monster first. By dropping a coefficient of 4 right in front of the water molecule on the left side, our oxygen atoms beautifully balance out to 4 on each side of the scale. Success! But notice the ripple effect we just caused. We kind of temporarily messed up our hydrogen count. 4 times 2 gives us 8 hydrogens on the left, while we still only have 2 hydrogens just sitting there on the right.
And here is where we complete the hero's journey. We look at that iron and give it a nice coefficient of 3. Then we look at our brand new hydrogen imbalance and just drop a coefficient of 4 in front of the H2O on the right side. Let's do a final check, nice and slow. We've got 3 irons on both sides, we've got 8 hydrogens on both sides, and drumroll, 4 oxygens on both sides. The scale is perfectly, incredibly, satisfyingly balanced.
I just want to pause for a quick second here and share a quote from our sources. Keep learning, keep practicing, keep growing. Balancing chemical equations is a skill, exactly like learning how to play the guitar or practicing for a big game. The more you do it, the more intuitive the math becomes. Consistent practice takes this from feeling like a really tedious chore to becoming a super fun, rapid-fire mental exercise.
Section 1. expert tips and tricks, advanced strategies. All right, let's keep moving.
Now that we have the fundamentals completely locked down, let's step it up a notch. Think of these 3 pro tips as essential weapons in your chemistry arsenal. Starting with the most complex molecule naturally simplifies the rest of the puzzle for you. Keeping polyatomic ions together saves you from immense counting headaches, and using temporary fractions, that can instantly unstuck a really stubborn, complicated equation. Let's look a bit closer at those last 2.
So let's apply that polyatomic ion tip. Look right here at the chlorate ion, ClO3. In reactions where these polyatomic groups stay together from the reactant side all the way to the product side, you don't even need to tally the chlorine and oxygen individually. Just treat the whole group as a single solid unit. In this example, potassium chlorate decomposes into potassium chloride and oxygen. By looking at the chunks, balancing becomes an absolute breeze. You literally just drop a 2 in front of KClO3 and KCl and a 3 in front of O2. Done.
But what about fractions?
Well, in the synthesis of ammonia, you might actually find yourself needing a 1.5 just to make the hydrogen balance temporarily. And you know what? That's actually a great stepping stone. The trick is, you cannot leave a final chemical equation with a fraction in it. That's a huge no-no. You just mathematically multiply the entire equation by the denominator to get clean whole numbers, which gives us this beautiful result. N2 plus 3H2 yields 2NH3.
Section 2. Real exam practice. Test your skills. Let's dive into some application.
It's one thing to look at theory, but it's another completely to face down a real-world scenario. Check out this actual past word problem from a board exam. Sodium reacts with water to form sodium hydroxide and hydrogen gas. The very first challenge here isn't even the balancing math, it's translating the English into a skeletal chemical equation. I want you to imagine doing this in your head right now. What are the chemical formulas for these substances? Take just a couple of seconds and try to build that out mentally.
And here is the final balanced solution. We get Na plus H2O yields NaOH plus H2. To balance that out perfectly, we need a coefficient of 2 in front of the sodium, the water, and the sodium hydroxide. Now, a totally crucial point to remember for your exams is that you might find mathematically larger combinations that still technically balance the atoms, right? Like putting a 4, and a 4. But you must always find and use the minimal possible whole number values for your coefficients. Anything else will literally cost you points on the test.
So, we'll wrap up this explainer with a little thought experiment just to test your fundamental understanding. What kind of chemical disaster might occur if you broke the golden rule and altered a subscript instead of a coefficient while trying to balance an equation? Well, imagine trying to balance the life-giving oxygen we all breathe, O2, and accidentally writing down O3, which is ozone. Suddenly, instead of a nice breath of fresh air, you've just created a toxic gas. So please, keep practicing those coefficients, relentlessly protect those subscripts in their literal boxes, and keep exploring the amazing puzzle